Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense systems DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
Well, good morning, afternoon, evening to everybody. Thank you for joining us so far. My name is Brian Benish with DSIAC. Appreciate you all being here today for this webinar presentation. Just a quick couple administrative notes while Andrew is bringing up his slides for the presentation. The format for this webinar is that Andrew, as soon as I'm done this introduction, will be delivering his presentation for about 30 minutes or so, and then we will do kind of a live Q&A. Therefore, at any time during the presentation, if you have any questions you would like to ask Andrew, if you were dialed or if you were joined in the webinar via the online platform, there is a chat icon at the top middle of your screen that you can use to ask a question. So you click on that, type in your question, and submit it, and we will work through them in the order that they are received. So again, any questions during the presentation, get them in queue, and we'll go through a Q&A at the end. I do want to quickly distinguish that from the chat feature that would be on the left-hand side of your screen. That if you do have a question, we'll monitor that, but I really want to encourage you that if you do have a question for Andrew, to make sure it's submitted through that question portal or form. The other item to note is that if you do have any technical difficulties during the presentation, rest assured, we're recording the presentation. We'll make that available to you after today, or maybe tomorrow, day after. And then the other item, if you do have any technical issues, is to note that you can dial in using the phone number that was provided with the registration. And if you are dialed in, you can then download the slides in a PDF format, at least, from our website. You can just go to DSIAC.org, go to our webinars, find the web page for this particular webinar, and there you will find a hyperlink to view the presentation slides. You can download them and then follow along with the audio if you are dialed in. And then last bit of advice, if you run into any other issues, you can email contact@dsiac.org, and a real human will be behind the scenes to help you out as quickly as we can to solve any problems. So I think that covers the bases on the logistics, the administrative pieces. So I will waste no further time, and I will hand the microphone, so to speak, over to Andrew for his presentation. So Andrew, floor is yours.
Thanks, Brian. I just want to do a comms and video check to make sure everybody can hear me and see my PowerPoint slide, my title slide up on the screen.
Yes and yes.
Excellent. Awesome. Well, then I'll get into it. Yes, so I'm Andrew Twaddell. I'm the project lead for this human agent interaction for Intelligence Squad Weapon project, or Intelligent Weapon Systems. The names kind of bounce around. We're out of the DevCom Army Research Laboratory, And for those maybe unfamiliar with ARL, we are kind of exactly what it says we are. We sit under the Army's Futures Command and are the Army's research laboratory. We perform basic and early applied research to ensure these military capabilities that are needed for the future fight are there when the time comes. And so that spans all all kinds of research areas, including kind of my area. This is the humans research side. There's materials. There's machine learning, computer science, and we partner with academia just as much as we partner with industry and other military centers, depending on the discipline area. So there are a ton of collaboration avenues open to us to connect the right people to the right research to advance our warfighting capabilities. So to me, the webinar has like a tutorial connotation to it, like I'm going to be teaching something. But really, my intent is to kind of inform the audience of the type of research that we're doing here, spark some good conversations and maybe new relationships. In the beginning, I'll give an overview of our problem space. But after that, I pretty much just got a series of videos kind of showing off our research to hopefully keep you all engaged. So having said all of that, I'll get right into it. Um, this specific research program, the Human Agent Interaction for Intelligence Squad Weapon, was built around the Army's vision for the next generation squad weapon, which, their goal is to enhance dismounted soldier lethality with individual weapons through on and off-board AI in the form of intelligent fire control systems. So when I say fire control systems, I'm kind of referring to broad mechanisms that seek to increase the probability of hit when firing a weapon, or probability of successful engagement is a broader kind of definition for that. You can imagine things in the dismounted realm as automated target handoffs between members of the squad, or augmented triggers that only allow you to fire the weapon when the optimal ballistic solution is obtained. All those, you can imagine quite a few different ways that you can define fire control. But these technologies that the Army wants to implement in the future, especially in this mounted domain, are predicated on accurate and robust aided target recognition, or AITR, ATR, as you'll hear it said. ATR is defined kind of computer vision algorithms that seek to detect and track objects of interest in imagery data. And so when you think of bounding boxes to calculate ballistic solutions for the rifle, that's what we're referring to here. But this ATR, AITR suffers a lot of the same shortcomings that AI in general does. So it can be brittle when faced with new environments that it's not trained for. It takes a very large amount of extremely difficult to obtain and expensive to label data. So if you think in an operational theoretical here, a dismounted unit is deployed to a region that we have not been to before, and we have no previous ground level data for it. And this region looks nothing like what the computer vision algorithms, the intelligent systems have been trained for. Or worse yet, adversaries can modify and know how to modify their appearance in such a way that breaks our algorithms, right? So essentially making our fire control systems useless, making our weapons somewhat useless, right? And so we need to kind of find a way to adapt to the environment. So I kind of use this image here, an example of our broader, longer term strategic goal. Moving from an approach where we're trying to replace the human with AI completely for operational tasks, to an approach where we're actually the human is actually being leveraged by AI to adapt AI. And so that concept is where this project kind of begins. And so with the specifics here, our goal as researchers and experts in human behavior here is try to investigate and ultimately leverage the innate capabilities of humans and human cognition in complex environments like a military battlefield, right? So that we can address performance gaps in AI, specifically for us, is these entire intelligent fire control systems. So here's where the term opportunistic sensing comes into play. And you'll hear me say it a lot. You'll see it a lot in this slideshow. And in some research areas, you'll hear it as ubiquitous sensing. This concept is pretty ubiquitous throughout this human AI interaction research area. And so kind of to define it here, we'll say the act of obtaining data for AI derived from tasks that the human is kind of already performing in a quote unquote natural environment without requiring explicit actions from that human. And you can imagine why this is very important in a military scenario. We don't want to negatively affect what the soldier is trying to do with their weapon by asking them to correct mislabels for an AI or push extra buttons, speak to somebody about something. We kind of want to just be able to draw their natural behaviors from their interactions. And so the rest of this presentation will kind of be about the four sub areas you see at the bottom, basically how we are trying to use this concept of opportunistic sensing to use the soldier to adapt fire control in AITR specifically. So the first two bullets down there kind of have more direct impact on AITR algorithms themselves, while the last two have more broader implications on how we deploy AI in the future military. Let's see if it'll play. There we go. So up until now, I haven't really given a real concrete meaning to performance gap in regard to the AITR for fire control problem. This is a video representation of one of the issues that's kind of persistent throughout not only AITR technologies, but computer vision in general, where a model isn't trained to recognize a certain situation. And in this one you're seeing is a partial obscuration problem. The target of interest is partially covered in some way where it's no longer recognized the model to be what it is. So this is from our own M4 platform with a FLIR EO camera on it. But we have replicated this kind of failure with other commercial systems like the Israeli Smash system, which is popular right now. What you'll see is that the bounding boxes disappear once it goes behind this slatted fence, which breaks up the outline in such a way that the models no longer recognize it as an e-silhouette. And yes, granted, now we know there are very sophisticated computer vision models that can probably overcome this specific scenario. But the broader point I want to make here is that there will be, and there can be, we will hit situations where an unknown environment arises and it's just been untrained for before and our models are not going to work. But one thing you may or may not have explicitly noticed here is that the human holding the rifle camera was able to continuously and positively track the target behind the fence even when the AITR failed. So the person was capable of contextualizing, oh, the target just went behind a somewhat see-through fence. I understand that the target's there. I can still understand that it's still moving in this direction. So with opportunistic sensing, how do we capitalize on that? So kind of the first step we needed to take is to see if we can even distinguish certain operationally relevant, marksmanship relevant soldier weapon behaviors. And our point was, can we do this based on sensors that are already on the weapon and in such a ways that we don't need any explicit button pushes or lever flicks from the shooter to do this? So for this program, we developed a live fire research platform that kind of mimics that instrumentation that's going to be present in the next generation squad weapon, their fire control systems. Aside from the obvious EO camera, right? Our primary sensor of interest going forward for this presentation was the inertial measurement unit, a device that can collect acceleration and velocities or movement profiles of the object it's attached to, i.e. the rifle here. And so you can see a schematic of what we're of the live fire platform that we kind of mocked up here for our experiments. And we set out to also mimic two well-established research areas. One you'll see there is human activity recognition. which is a very large research area, using IMUs, not just IMUs, but other sensors on a human person as well, to use their movement to classify their actions. And you'll see a little bit more of that in detail coming up, but also mimicking eye tracking research. So kind of leveraging the experimental paradigms that you see quite often um, in that research, where certain eye movements have been shown to be related to certain visual cues. So we can kind of think of the rifle, what they're doing with the rifle, and viewing through their scope as an extension of their eye movements in this case. So there's the schematic of kind of what going forward, the platform we're working with. Let's see here. And this is just an overview of our initial kind of pilot experimental methodology for collecting weapon soldier weapon movement data in a flat range kind of constrained scenario, and applying machine learning to classify specific marksmanship's behaviors that we think are going to be critical to provide context to AI. So on the left, you have, kind of various IMU data streams, velocity and acceleration, showing how different actions that we had them do. So smooth pursuit or tracking of a target as it's moving, transitioning between targets. So we'll see in a little bit as well. And on the right, you'll see kind of the discrete action labels that we were able to manually pull from this IMU data. And with this initial data collection and post hoc analysis, we were able to run pretty accurate random forest classifier on the time series data to accurately predict which classes of weapon raise, static aiming, where they're just holding their aim point on a static target, not moving, transitioning, so quickly moving the scope, the rifle, from one target to the next laterally, tracking, so smooth pursuit, and weapon discharge, so actually firing the weapon. That's a pretty big energy pulse and pretty easy to pick out from a classifier standpoint. Or there's the majority class, the null, the trash, the garbage. It doesn't really refer to anything critical to the marksmanship behaviors that they're displaying. Not to say that we wouldn't use it at all. It could be used great as a negative case for some of these machine learning classification models. So it's much better to just show y'all. This is a video presentation of that flat range data collection with our human activity recognition, or these classifier models actually classifying the action that the soldier is performing. So you can see the ESIL previously, like it was doing before, sliding to the right or moving to the right, and the soldier is actively tracking it as it moves and as it goes behind the fence. And you'll see in the upper right quadrant in the bottom, or the upper left quadrant in the bottom right, you'll see kind of the classifier label that's being spit out by this random forest classifier, this machine learning classifier that we've implemented here. And we've gotten this in real time as well. So there are concerns of overtraining with this very constrained and very restricted paradigm that we've collected this data under, but we have been able to show relatively good results in real time as well using the same models. So there we go. So we have shown that we can actually discern these behaviors, and we can understand a little bit of their relationship to certain marksmanship behaviors that are critical, that we think that AI is going to need to know. So what I've got here, this is pretty much where I start the series of videos of how we're approaching this problem of the breaking AITR for fire control with the human at the center of our approach, this opportunistic sensing for this interaction. Stabilizing tracking algorithms, so the computer vision algorithms with multi-sensor fusion. We'll see the IMU come into play even more there. Unobtrusively collecting in-field data for rapid labeling. So we call that the ad hoc learning, so almost learning on the fly in the field, and we'll show a good video of that as well. And the bottom 2, 3, and 4 for the more global implications for how we deploy these AI approaches in the field. So we'll just go right through another video. Let's see. So here we have the is a YOLO V3, I believe, computer vision algorithm detecting a human and tracking them in the field of view of the camera. You can see the barrel on the left there of the airsoft gun. So this is attached to the Picatinny rail of a mock-up M4. And so as the person of interest walks behind, here, I'll start over. Becomes partially occluded by this object in the environment, the AITR system drops it. You see the bounding box kind of freeze up, and we use that as a cue for the IMU to take over and help stabilize that bounding box and lock it in the kind of the field of view or in the environment, so to speak. Um, but I think what's more interesting is what this next portion of the video is, where we use the IMU to kind of lock the bounding box in the for the aim point in the field of view of the camera. So it's the same situation. Um, the person of interest gets partially obscured. The AITR doesn't know what's going on. So now the shooter is kind of in control of where the bounding box is looking based on the IMU. So what we can do from here is maybe leverage that. So this is part of the ad hoc learning or the rapid labeling and model integration. This is just an example from, we pulled the flat range data collection that we collected earlier. And what we're trying to do is, this is YOLO V3 as well, except we've kind of reduced or cleared the model set that the algorithm is looking for. So it doesn't really know what it's looking for. There's no training set in the model for it to look for. But we see the ESIL kind of doing its thing on the left side, and the soldier positively tracking it. On the right side, with the kind of green and red in the very center of the field of view, what it's doing is it's basically pulling those pixels based on where the soldier is pointing, using the cue, so we know that the soldier is tracking a target based on their behavior. So we know that roughly the pixels of interest are going to be in the center. So now we start pulling those. And in the bottom right corner, you see kind of this data augmentation and training iteration loop that it's going for. You see the colors and the shapes and the colors, the shapes change as it builds its model further and further. And so in the next iterations, you'll start to see the bounding boxes kind of build, and the model starts adding more training or adding more model sets to what it's looking for. Hopefully I can kind of zoom through. This is a longer video. No, my thing's in the way. So eventually I'll get to it. So where it didn't see an ESIL before because it wasn't trained to look for an ESIL, now it's got the data support behind it to recognize an ESIL. And you'll start to see on the right side, this detection frame here, the bounding boxes start to appear as it runs over the video. There we go. So after the first one or two iteration trainings, it's still the probability of it detecting is pretty low. So you'll see the bounding boxes go in and out. But as you do more iterations of training like this, you collect more data, your accuracy is going to get greater and greater. So we're really trying to reduce the cycle, speed up the cycle of development for these computer vision models, so that maybe we can get in-field interactions to inform almost real-time model development for our soldiers and the fire control systems they're using. So kind of this is the subsection number 3. So that's all good for these, like we said, tight, constrained experiments that we've been kind of working with so far. But we really also need to be able to push this out to create other pipelines to collect more dynamic target engagement scenarios. And we're really trying to leverage commercially available technology. So the platform we've put together so far was our own research platform, so we can configure it how we need to. But we need to be able to get large amounts of sensors to collect large amounts of data for these AI solutions. And so what we've been trying to do here at ARL, I'll start on this mounted side here, partnering with commercial vendors. This is with FN America. They have a kind of training and simulation unit that is the same. It's got an EO, black and white electro-optical camera, along with an IMU in its system that attaches to the Picatinny rail. And it allows for continuous collection of weapon movement and imagery data. So what we've been able to do with this pilot force on force scenario that we put on at Aberdeen Proving Ground up here in Maryland, collect this data in more realistic scenarios and see what we can do with it. And so um, with the IMU data synced with the EO data, what we've been able to do is use the behavioral cues in the IMU data to select frames or reduce the number of frames we have to manually label or manually check. So granted, this was a very small pilot study. This is not an easy thing to do if you're not part of the training units out there in the Army. So with the limited number of sensors and soldiers we had, we were able to collect about 30,000 frames total during active engagement. But using the behavioral clues, we siphoned that down to only 3,000. So that's a tenfold decrease in the number of frames that are actually of interest to us based on are they pointed at an adversary. And so we go with that. You can see the manually labeling of a target on the right side with the red bounding boxes through this kind of engagement. So in a more general sense, this approach can also be developed for the mounted domain or vehicle domain. So what we've been able to try to do is replicate that using fire control systems within vehicles. So we were actually able to, fortunately enough, go out to National Training Center in California, where their opposition force, I believe that's the acronym for it, but they're the training unit that acts as the adversaries during exercises for our cavalry, other units to train against. And so by collecting how they're using their fire control systems within their vehicles, they are how they're zooming in with their camera, pressing certain buttons. Those are behavioral cues that maybe we can leverage the same way. And so we're currently in the process of fleshing out that part of the project, working with Kinetic, and they have a target engagement video capture system which captures all that metadata, that behavioral interaction data, along with the EO and IR data. And so not only could you use that for developing computer vision models, but training units may be of interest to that too. Is like when you go back for after action reviews, AARs, when a training unit says, okay, you did this at this time, what was your thinking? It can provide better training material for those units. And so that's part of the research program that we're looking to expand into as we go forward in the next couple of years, is really fleshing out these pipelines to get better, more dynamic, more complex data, and see how we can implement these opportunistic sensing approaches. Okay, and so for the last part here, human autonomy teaming approaches for mixed squad small arms ecosystem. So we're back kind of referring to that picture that I showed earlier of our more long-term strategic goal, where now you can start adding behavioral context of your soldier and your squad of soldier, your teams, platoons into this AI or autonomy ecosystem. So how can we demonstrate these approaches in this teaming approach? And so two different kind of use cases that we're looking at right now is wind estimation use case. Now, this is much more related to the fire control systems that we talked about earlier, where wind is still a large unknown factor in ballistic kernel calculations, right? And there's no current standard or automated implementation to correct or display disturbed reticles to a user of a weapon so that we can increase the probability of hit. And so the second use case for us is this kind of decision dominance for multi-domain operation, MDO. Now you can start aggregating these behavioral cues together to derive emergent behaviors across the squad that may go to inform decision-making aids that are actually back at off the front line at a tactical operating center, being used by command control, commanders to make tactical decisions over larger units. So currently, only limited behavioral or environmental cues are being implemented in these kinds of environments or these kind of technologies. And so what we've been able to do here, let's see, slow to respond, start syncing and connecting all these, the human aspect of the system with the rifle, and also these other autonomous assets like a UAS. So here, let's see if I play the video. So what we have in the top row here of this video is the culmination of the different research, different components of the research we've been doing with the rifle. So on the left side, we see the behavioral classification of the shooter, what they're doing with the weapon, and the third from the left, you see the camera, the imagery data coming from the rifle, similar to what we saw before. It's got the computer vision algorithm detecting faces. So you see the picture in the background, it's picking that up. But when the face gets obscured by the person, we're just covering the camera with our hand, the IMU takes over, the bounding box gets locked, and we use that, from that point forward. You see the weapon orientation data coming in from the right. That's what we're using to classify whether the soldier is tracking, transitioning, static, all that stuff. But this is all being collected and synced up in conjunction with a small UAS being flown nearby. So you can see the video footage of on the bottom left there, the computer vision algorithm of the UAS is being picked up in the environment, and we're also getting the wind estimation. So the drone, the UAS, is collecting and distributing that wind estimation data to the rifle system. So now we have a way to possibly connect these different intelligence systems together to again improve the lethality of these fire control systems. Now maybe we can display a disturbed reticle to increase the probability of hit for some of these things. And there are a number of different a number of other applications for this sense. When you think about counter defilade situations where you have adversaries hold up behind an obstruction, that now you can share context between a UAS that's doing a search out in the field back to the rifle, the human holding the rifle, behind cover. So now we can start really looking at human autonomy teaming in these really complex scenarios. And that's kind of what we've done here. So this Acropolis, what I'm going to talk about here, so autonomy, cross reality, operating picture, Optempo, learning information sciences is an ARL tech demonstrator for low TRL, so technology readiness level. So more basic research, plus 6.1, 6.2, if you know the designations. So a demonstrator for advanced technologies and human agent interactions to enable situational understanding for not just individual soldiers, but squads of soldiers and platoon level, for feeding into company level operating standards, what I was referring to earlier. When you start aggregating these behaviors, you start deriving emergent properties across larger groups of soldiers, and that could be used as context for commanders to make tactical decisions on. And so this was in conjunction with some other groups at ARL, the UAS. We have a UAS team, as well as a computer science team that works on cross reality or VR, AR, common operating pictures, COP, so that we can get shared situational understanding to higher echelons, essentially. And I can go into more detail for any more of these subjects with follow-up questions. But so these are just to reiterate, these are what we've been able to show with this opportunistic sensing approach of really leveraging the soldier behind the weapon to improve, some performance gaps we see in AI, AATR for intelligent fire control systems. And so we've been able to fill those cases, provide context for enhanced learning and model development. We've kind of shown in the last two bullet points. And so what we want to do in the near future is start assessing the trade-off. So when we start feeding information into the scope for the soldier to use for fire control and such, how is that going to affect their actual performance, right? You think of cognitive overload is a major concern with these kinds of VR, AR projections to people. And also, how do we incorporate other opportunistic sensing modalities? So far, we've just been kind of implementing this, or specifically our specific application has been with individual rifles. But now, if we start synchronizing with other technologies like heads-up displays, how can we start leveraging those connections in autonomy as well? And then again, kind of really expanding our ability to continuously collect and label new data coming out of those, training units that are always adapting their scenarios to what's out there for that our adversaries are doing. And so that's kind of our near term, in the next couple of years, how we're expanding our efforts in this research area. And that is actually my last slide there. I'll keep the slides up, but I know I talk fast. If there are any questions from the audience, or Brian, if you want to take over from there.
Yep, absolutely. Thanks, Andrew. It was a very nice presentation. We did have a couple questions come through via the chat, some through the question portal. So I'm going to go ahead and I made sure that the ones in the chat were copied over. So I'm going to go ahead and just dive into it.
Yep.
Maybe before I do, I'll just remind everybody it should be a chat icon image at the top middle of your screen. You can click that, enter your question, and get that in queue. So that's where we're going to go next. Looks like, Andrew, do you mind? I think it needs you to stop sharing your screen.
Oh,
so I can take over.
Apologies. Yeah.
Turn that off. Yep, there we go. All right. So the first question we have just kind of generally says, how do devices, how do they communicate, interface with the end user? Is this audio, visual, or mechanical?
So with the rifle specific application that we're looking at, it is primarily visual through optics. The optics, a lot of where the next generation squad weapon, development is going is the kind of AR projection in the scope for the soldier to see as they peer through the scope of the rifle. So that's where you might see the AITR bounding boxes pop up so that the soldiers can be aware of targets in the environment. However, like I said at the last slide there, we are looking to expand this into other modalities as well. So you can imagine a heads-up display. If you're aware of IVAS program within the Army, which is their next generation heads-up display, which is to kind of incorporate AR into the eyewear for the soldier, but also has tactical radios. So we've been focusing on visual projection. However, there's all sorts of directions we can go with the research from here.
Okay, very good. We do have a question on IVAS coming up, so appreciate you bringing that one up. All right, our next question is referencing Joe Rexwinkle, a biomedical engineer for the ARL, saying he's working on a similar topic. So the question to you is, if you were familiar with Joe and his work, in particular, he's using data from M1 and M2 training data from out at Fort Benning.
So I am very familiar with Joe Rexwinkle. He is going to be a collaborator on this project going forward because of his similar interests with the training data. I think he's working on from the mounted side, the vehicle side for some of his stuff. But there is a large amount of overlap in what we're trying to do and what he's trying to accomplish as far as like the data perspective. So yes, I talk to Joe Rexwinkle almost every other day.
Very good.
And if we want to follow up with that, we can definitely get together for further conversations.
Good. No, I'm glad to hear the dots are connected. I think that's the win. All right. Next question. Could you give an example of an emergent behavior that you expect, at least in the wind estimation use case?
So maybe I misspoke or didn't say it quite right. I think from an emergent behavior perspective, what I see it's more of a squad level human behavior concept. Once we understand, right now we have shown that with an individual soldier and an individual weapon, we can classify and tell what they're doing with the weapon, tracking a target. However, if you think you can start getting these these systems on multiple soldiers, and you can start expanding your understanding of the battlefield in front of them. If you have one soldier have a statically aiming on, over here in this region at something, that's a cue that it may be of interest, but this soldier on the other side of the field is quickly transitioning between targets. That kind of information can be very useful to how, a commander is pushing his tactical units out onto the field. So when I say squad level emergent behaviors, is like aggregating the actions of what the individuals or soldiers are doing to get a better idea of the battlefield. So from a wind estimation use case, I don't know that that really connects for me. Maybe I misspoke and conflated them when I shouldn't have. But wind estimation use case is it's um, quite straightforward compared to the other concepts here, where just projecting a disturbed reticle. So you have your aim point that maybe your soldier is looking through the scope and sees his aim point, but that aim point is not going to be the point of impact a lot of the times, based on a lot of things that the ballistic solutions solve for. And so if you add wind, like we know we have a wind variable into that equation that wasn't there before, maybe we can push that reticle to where the soldier is going to point it where the ballistic solution thinks the soldiers the bullet is ultimately going to land. So yeah, two different things in my mind, and I hope maybe that cleared it up.
Yeah, definitely. I think help clear it up and deconflate them.
Yeah.
All right, next question. So can the bounding boxes be shown in AR on the IVAS headsets that the soldiers wear?
Absolutely. We are currently, because we are, lower down on the technology maturation level. So as far as research, we do have upcoming efforts looking at the HoloLens, which is, the more basic commercial version that the IVAS is kind of to replicate in a sense, or has replicated, or maybe uses. I can't remember exactly which system, but our effort is to start syncing the system. So yes, IVAS does have the capability, or HoloLens, excuse me, has the ability to do bounding boxes in AR as well. And we're looking to sync that information with what the weapon is seeing. So maybe they are in the environment, the heads up display like IVAS and the weapon are noticing or seeing two different things. How can we use or leverage those in continuity, discontinuities to better understand the battlefield?
Gotcha. Very good. All right, got some more questions coming in, so let's move along. Next question is asking, how complex can your models become before they can't run in real time?
Oof. That is not something we've really been pushing. In fact, so I can't answer one way or the other as far as the complexity, efficiency trade off there. We did implement, as far as the time series classification on the movement data, we did keep it very simple for that reason, to be able to run it in real time. So random forest classifier, relatively lightweight compared to other. If you start talking about neural networks, starting to implement those, you're going to run into low swap, low size, weight, and power restrictions for computation, and that's not something that we've been looking at really. That's something that a higher technology readiness level center that we would transition this information to would start investigating. So I'm not sure.
Okay. Fair enough. Next question. Are there correlation algorithms that exist or that you have tried that will attempt to find commonalities between frames to determine tracked object rather than having to train a machine language implementation?
Sorry, I'm rereading here, so I make sure I
Yeah,
understand.
hopefully it gets it all
Yeah,
together.
are there correlation?
Correlation algorithms to find commonalities
Frames
between
to determine.
frames rather than training a machine language.
I mean, that is certainly possible, and with our data set, given that we've only um, looked at e-sills or e-silhouettes, the outlined targets before, I'm not that would be kind of an easy problem as far as commonalities because they're roughly all the same shape and all the same size at that point. But with the more dynamic force on force data collections that we're hoping to go for in the future that I was talking about at the end, you can start asking those kinds of questions. So we want to tee up the ability to ask those kinds of questions with our approaches. So I'm sure it can be done. We haven't dug too far into it.
Okay. All right. Next question: are there plans to link the training of multiple I guess modals across modalities via federated learning?
Plans to link the training of
With
yes.
models, yeah. Are there plans to
Yeah,
link the
yeah, yeah.
training of multiple models across modalities via federated learning?
So I'm not sure about the federated learning. That might be a little bit out of my purview here to talk about it. But yes, referring to earlier when we were talking about the modalities of, we have eye tracking abilities with a HoloLens IVAS like heads up display, or now you with a synchronization with the UAS, they have their own computer vision models that they're looking for. However, it's a little bit different perspective. So how do you kind of um, aggregate those models together in a way for better context? It's something we are that is the next step of this basically. So now we've kind of fleshed it out with the rifle. Let's start adding in different component technologies as well.
Right. Okay, very good. Talked earlier about wind estimation. The next
Yeah.
question is kind of specifically about that. Could you kind of maybe essentially expand on that, or what are your thoughts on the accuracy of wind estimation?
Ooh, it's difficult. And in a where we have been doing it in an uncontrolled kind of environment where we're just at the mercy of the wind of our range, essentially. It's hard to get good accuracy measure. It's hard to get enough variation in measures to determine accuracy. I know we are. I feel like I'm saying this a lot now. That is something we are starting to expand into in the next couple of years. I can't give a number to what we've been doing so far. That's more of it might be more of a technical question for our UAS team. That again is out of my purview.
Okay, fair enough. All right. Next question is just generally asking if there is any collaboration, I suppose, with your group and DARPA or IARPA.
We haven't specifically for this project or this group. But if
Okay.
you know of teams interested in collaboration, please reach out.
Yes, yes, I will second that. I mean, that's as you kind of mentioned in the beginning. This is one of the reasons we're doing this presentation. We want
Right.
opportunities for collaboration and kind of get the word out.
Exactly.
So,
So I will say, to kind of correct myself there, the past couple of years have been a hyper focus on these individual weapons, next gen squad weapons. So a lot of our collaborations, and if anybody's on the line here from the JSAP office, Joint Services Small Arms Program, that does the kind of R&T portfolio management of small arms across the DoD. There have been our primary collaboration partners with linking the different research groups. But as we expand into broader and broader research areas here, I think folding in DARPA and IARPA are going to be critical.
yeah, okay. All right, and I think the next question is the last one we have in queue. Long-ish one says, have you considered developing the AI to be sufficiently advanced to identify and distinguish target behaviors? For example, prioritize a target whose gun is pointed at you versus a target who is running away.
So this is an interesting research area, and I will kind of agree with you that what we've been looking at, you think of like 2D biomechanics, which is like trying to derive posture and movements of a person from a video based on bony markers that you may be able to track on the person. So, and then we talk about posture can convey intent. So in a scenario for individual weapons, you can see like if a person in the field of view of the camera is hunched over or doing some behavior that can be conveyed as malicious or that more immediate threat that they have a gun, um, that there is a group out of DevCom Armament Center who is within the Army. They're in DevCom as well. They are looking at that question, and so there are groups that we're knitted with that are looking at that two-dimensional biomechanics question for target intent and target behavior that we're linking with, but we aren't doing it specifically with this. But again, the data we want to derive or the data we want to be able to continuously collect with our pipelines at these training units can just go to continually feed and feed and feed more data to get better and better models.
Very good. Well, fortunately, when you were replying to that, we did get another question that came in. So move on to the next one. It says, so what kind of skills do you envision that a soldier would need to effectively use this autonomy? So perhaps a training related question.
Oh, that's a good question. I've been kind of coming at it from the the opposite perspective, is like, what can we do to raise the floor of kind of the average soldier, right? So not that they actually need to be trained with a specific skill or anything like that, but our technology is developed in such a way that they don't need that skill. We are kind of using the AI to enhance their performance without them having to train for a skill, right? Like the automated target recognition or automated target handoffs are doing that kind of situational awareness skill set for them in a way. So I think I coming at it from a different perspective of raising the floor of the average soldier as opposed to imbuing some kind of skill on them. But that's definitely area that a lot of Army centers are looking at as well. The trainings, STTC Simulation Training Center down in Orlando are very interested in those kind of questions that we have connections to as well.
Perfect. Yep. I concur. Right, we're trying to make it that much easier for the soldier than burden them with other training.
Yeah, exactly.
All right. Well, the last question I will answer. I think it's a good kind of closing question. This person joined halfway through. Will the recording be available later? Yes, and we'll get that out, link out to everybody tomorrow, if not Friday, and so that will be available. Worst case scenario, it'll be posted through on our website where the webinar is listed, so you can access it that way. And so with that, I think we will close out for today. Andrew, thank you so much for the presentation. I thought the Q&A at the end was great. Appreciate the real-time feedback and responses to all of those questions. And thank you to everybody else who has joined and participated.
Yes, thank you, Brian. This was the engagement was very good, and I hope some of my answers and maybe non-answers were satisfying for the audience.
Yes, absolutely. All right, well, everyone have a great rest of your day. Thanks.